So, Machine Level Programming 5. Advanced topics. All right. Okay, so we talked about structures and alignments last class. I'm going to go ahead and skip past those slides. I think we've got those in here just to provide some overlap for Seth, who was lecturing earlier in the day, because he was not here earlier in the week. Let's talk about unions. You know, anytime you look at an Intro C book, right, there's like a section on structs, and immediately following it, a section on unions. And you know what? They look a lot alike in syntax. But they really don't have very much to do with each other at all. So a struct is an aggregation. Okay? Puts a whole bunch of different types of things together so that we can describe something whole. Like a person record, right? We can have a first name and a last name and an age and a date of birth or whatever, all put together into one type. A union is completely different. A union allows us to have one of several things. Okay, or one of more than one thing, technically. Okay, so if I take a look at this union, union U1, union 1, it has a character C, an array of two integers known as I, and a double known as V. Okay, and now we have a pointer to this that we're calling UP, union pointer. Now, if we ask ourselves, how big is this union? At any point in time, the union contains either a char or an array of two integers or a double known as or a double. Okay? Not all three. So the size has to be the size of the biggest among these things. Okay? A char is one character. An integer, let's say, is a char is 1 byte. I'm sorry. An integer, let's say, is 4 bytes, so 2 of them is 8. Okay? Or a double is 8. So this has to be big enough to hold something that's 1 byte, big enough to hold something that's 8 bytes, or big enough to hold something that's 8 bytes. Right? So it has to be at least 8 bytes large. Does that make sense? Now, since it's only holding one at a time, it has to, it doesn't need to be more than 8 bytes large. Right? So that's what we see here. That's what this picture is trying to show us. It needs to be big enough to hold any one of those three things: the character, the two integers, or the double. That's different than a struct, where a struct holds all of them simultaneously. One at a time, simultaneously. Okay? Why do we use unions? Unions are used for all sorts of reasons. The way they're used a lot in our textbook is basically as a way to convert by reinterpreting the existing bit patterns. I guess let me back up and rephrase that. A lot of times if I convert from a double to an int or something like that, right, the conversion is sensible. If I take 1.5 and cast it as an int, I get 1, right? That's not a reinterpretation that's not a reinterpretation of the bit pattern, right? We know that the bit pattern for a floating point number is completely different than the bit pattern for an integer. And if you take a look at those bits and just reinterpret them as an integer, you wouldn't end up with 1. You'd end up with some really weird value. So what a union allows us to do is put a bit pattern in as one type and then interpret it as another type. So it lets us reinterpret the bit pattern without doing a sensible cast. Okay? So that's one reason that we use them. It gets us around the type system. And you'll see it fairly heavily used that way a lot in, for example, your textbook. Because this is a course about low-level things, about looking at the bits. But you actually see them used in code in a lot of different ways. A common way of using them in code is to give you a cheap form of sort of inheritance. Okay? I might have a struct that has, where I'm representing something that has 5 common fields, and then this type, or this type, or this type, or this type. Okay? So anything that one can buy on a website has has an item number, a price, and a quantity. But products, tangible products, might also have a weight and a volume for shipping. Whereas services, like I'm going to come and clean your house, that doesn't make sense. Instead, they have a number of hours associated with them. Or they have a time window during which you can expect them, or something like that. So now I may create a struct that represents a product that contains the common fields, and then a union. And then any particular instance of this struct will contain either the versions of those fields for the actual tangible product, or the version of those fields for the services. Does that make sense? It's sort of like having a base class and two derived types. Right? I have the basic struct that contains the union, and then the union is A or B or C or D or E, and then it can be a specific type A, B, C, D, or E. You see this, for example, used in operating systems, where you have a file system, and every file system has certain operations. But then you have different file systems you might have. Right? You may have a union mount file system. You may have an ext2 or ext3 file system. You may have an XFS file system. All of which have the basic operations, but then they have some additional things that they do, additional features. And so you use unions to establish that. Okay? It's basically like having a base type for all file systems, and then derived types for each specific type of file system. The difference is by using unions, it's all known at compile time, right? Your code actually says your union is a union of A or B or C or D. No one can come back in and derive a new type later on. You see how these are often used? Does that make sense? Okay. So there we have it. Here's an example of how our book sort of plays with them. We take an unsigned type in, and we return a float. Normally, if we would cast from an unsigned type to a float, we get a meaningful cast. If the unsigned type was let's say 4, the float would then be 4.000 whatever, right? 4 would fit in the integer component of that float, and we get a meaningful cast. Well, here what we're actually going to do is we have this struct that we're putting something in as an unsigned type, and then we're returning it using the float type. So we're not actually ever going to cast that. We're going to look at it once when we put it in as an integer, and look at it again when we take it out as a float. And so there's never a cast. When we actually get that float value is going to be really weird, right? Because we're just reinterpreting the bits of the unsigned as a floating point number. So the obvious reason we do things like this, for the textbook, is this is how we create examples, right? If we're trying to create problems, we're trying to create examples that cause you to play with bit patterns, we'll use unions to test the answers. And that's the reason your book sort of, has this example in it, is because it's an example that was code that was actually written to solve a reasonable problem. What's the answer to the question? If I have this bit pattern, tell me what it is as an integer, tell me what it is as a float. What do? We use a union. We put in the bit pattern as hex, right? Look at it as an integer, look at it as a float.
Just a quick question.
Nope, put it away. Excellent. Thank you. Yeah?
Should the top box, for instance, in the left bottom box be bitfloat t as the type? Should the top box say type def bitfloat t?
So what this is doing syntactically, the question is, what's going on with the bitfloat t?
Right.
What's going on syntactically, if you think about a simple type def, a simple type def might be type def unsigned int to uint. So this is type def union blah 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 to bit underscore float underscore t.
Got it.
Does that make sense?
Yes.
Does that answer your question?
Thank you.
You're welcome. My pleasure, actually. Okay. All right, so we talked about byte ordering, right? We talked about big endianness and little endianness. This idea that, when we have something like an integer or a float or a double that contains multiple bytes, they need to be ordered in one of a couple of ways, right? You can order them, as we would count things, 1, 2, 3, 4, 5, with the biggest on the right-hand side. Or you can do it sort of as you would if you were counting the places in a number. This is, 10 to the 0th power, 10 to the 1st power, 10 to the 2nd power, 10 to the 3rd power, right? With the least significant on the right and the most significant on the left. And so when it comes to representing multi-byte types, there are two conventions. Big endian, which has the most significant byte at the lowest address, therefore the biggest byte at the biggest address. Okay, or little endian, which has the least significant byte at the lowest address. Okay? So here we can see that we have a union that contains a char, 4 shorts, 2 ints, or a long. You can see on a 32-bit system, these are all equivalent sizes, right? 8 characters is 8 bytes, 64 bits, right? 4 shorts, right? Each short being 2, that's still 8 bytes, 64 bits. Each integer being 4, right? Okay, so so now we have 2 integers instead of 4 shorts, same thing, right? 4 times 2 is 8, 8 bytes, 64 bits. Or we have a long, right? And on a 64-bit system, with that long being 64 bits, it occupies the full space. Here on a 32-bit system, you can see where a long is only half the size, right? That space is just blank. Okay, it's padding. Why? Well, the struct has to be created, the union has to be created big enough to hold the largest of these types. So in this case, if I'm dealing with the array of characters, the array of shorts, the array of ints, right? I need that full space. But if I'm dealing with a long, I can't shrink the union. So that's just padding. Okay? What happens if you put a long in and then turn around and try to read an int out? You've only explicitly written to these bytes. Now you're reading all of these bytes. What happened to these? Nah, your guess was 0 extension, which was a good guess. The answer is we don't know. But you guys should write the code and try it yourself. You shouldn't take my word for it, right? These are the types of questions you want to ask when you see an example about this, right? Hey, what happens to those things if I do this? Okay? If I write in if I write in an array of all null characters, and then write in some long, what do I see here? Now let's change the game to something that's going to give us a little better visibility. Let's say I write in an array, right, of all f's, or b's, or c's, or something that's not zeros. And now I write in a long. What do I still see here? The f's that I wrote, all zeros, something else. So you see things like that. Take a look. It's worth a dive. Yeah?
Are we guaranteed that the padding will always be on the right, or that the type will always start immediately on the left?
Are you guaranteed the padding will always start on the right? Yes. Okay. Yeah, and there's never a case where padding will come before something, either in a struct or a union. Okay. This is just an example. We've seen one very, very similar before. We showed the byte ordering. There's no real magic there. This is just a throwback to the big endian versus little endian discussion. Okay, we've had that discussion. Memory layout. Okay, so when you think about a process, there are a lot of different things going on in that process, right? There's the code that's actually running. There's the heap that you're allocating space on when you call malloc, right? And there's the stack that grows down automatically as you make function calls, right? There are global variables. There are constants. Okay. These things are organized into sections within the file. The lowest section is the text area. Okay? That has the program code itself. That has the executable part. It's readable and it's executable. The next thing we have is the data area. This data area is the data area for things that are known at compile time. Okay, for globals. It's not like local variables, right? Because those get pushed and popped off the stack. Okay? It's not things that are mallocked and free because those are in response to program behavior. These are our global constants. Okay? Now there are two basic types of global constants. Okay? Or not global constants, global variables. Okay? Or global values. There are constants. The thing about a constant is the value is readable, right? And it's known at compile time, but it's not writable. That makes a constant value a lot like the text area, a lot like the code. So if we think about a constant value, okay, where we have a variable x that's equal to 5, and it's constant, const x equals 5. X has to equal 5, right? That can be placed into a read-only page just like the program itself, because I can never write to it. So if you think about the program code, it's readable and executable but not writable. If you think about constants, in an ideal world, they're readable but not writable or executable. So if I have a program constant, I can do one of a couple of things. I can put it on the same page as my code, because it's not a big deal if it's executable. Nothing's going to try to execute it. Nothing's going to jump there, right? Or I can put it on another page just above my program, where I have all my constants, and mark them read-only. Now, if I think about initialized global variables, things like x equals 5, not const x equals 5, but like x equals 5, where I have a value that can change, I still need to read that value from my program, right? I have my executable file, and that's where x equals 5 is. So I've got to read that from my file into memory. So above the text area, which is readable and executable, but not writable, I have an area for values that are readable and writable, but not executable, and need to be read from the file. Does that make sense? Above that is another area. It contains uninitialized global variables. Okay? Uninitialized global variables are a little interesting because there's no value to be read, right? Int x semicolon. We don't read a value from that file. So the value, right, the variable, we need space allocated in memory for it, but we don't need to read it from the file. It's not being mapped in. So a detailed view of this has the text, meaning the code itself, followed by the initial constants, followed by the global variables that are initialized, followed by the uninitialized global variables. Some people call the part of the process's memory that stores uninitialized global variables the BSS. Don't ask me what BSS stands for. No one knows. It's been used in compilers when designating that area going back to the 60s. But no one knows who started it or why. They asked one of the people who wrote one of the early compilers, and he was sort of old and said he didn't remember. He offered some guesses. But no one really knows why it's called the BSS. That's just what that area is called. It's a little bit of history that's been lost. So we have the text area, the program code, okay? The constants, the initialized global variables, and the uninitialized global variables. Now, once the program starts going and we start to call malloc, we grow the heap. That grows up during execution. And as you know, we talked about from the top down, right? The stack grows downward. Right? Every time a function is called, we push onto the stack. Every time a function returns, we pop off the stack. Okay? Now, let me talk about a special case. Static local variables. What's a static local variable? Somebody help me out. What's a static local variable? You knew I was coming for you. You can see the guilty look. Okay, help me out. Don't know? Okay. Anybody know? Yeah. Good guess, but I'm not going to repeat it because it's not quite right. But good guess. You guys have never used static locals before? Yeah.
Isn't the scope limited only to the function that calls them?
What's that?
The scope is limited only to the function that calls them.
The scope is limited only to the function that calls them, but that's like any local variable. What's special about these?
You can't see them outside the function.
You can't see them outside the function. That's true of any local variable. Oh, we've got somebody knows down there. Yes, ma'am.
That's final in Java. Once you initialize them once, they can never be written over again.
Not quite.
They only get allocated for a function when one function is like done. It just like not be allocated.
Okay, they're only allocated for a function, but that's true of any. That's sort of true of any local variable. Okay, so you guys haven't. I thought you guys played with these in 122, but maybe not. So a static local variable is a variable that has the same lifetime as a global variable. That is to say, it lasts as long as the process does. But it has the same scope as a local variable. That is to say, you can only use it within the namespace of the function. Okay? So if you wanted a function that could count the number of times it was called, you could put in a static local variable, and every time the function is called, increment it. And it would remember the value from one call to the next. If you have an initial value for this thing, like you have some static local variable, static int x equals 0, it'll get initialized to that value just the first time when the process is loaded. Not every time. Yes?
Why is that better than if you were to initialize it as a global variable?
Well, the question is, why wouldn't I just use a global variable? Well, the answer is that I might not want that variable to be visible to other parts of the program. Minimally, it would pollute the namespace. If programs started using global variables instead of local variables, right, then you'd have a bunch of variables that, would then get confusing. Farther out, somebody might see a variable called count and think they could use it. And it would get confusing. The count of what? And people might misunderstand what it's for, try to use it for something, who knows? So what this gives us is it gives us the benefit of a global variable in terms of the lifetime. It can store a value between function calls, but the software engineering benefit of being inside the function's namespace, so we don't pollute the global namespace and can use it just where we want it. Does that make sense? So static local variables, because they have the same lifetime as a global, are part of the data area. Right? If they're initialized, they're part of the regular data area. If they're uninitialized, they're part of the BSS. But they're basically global variables in the namespace of a function. So you can't use them in a different function, but they do retain their value between function calls. Okay? If we take a look at this, big array is a global. Huge array is a global. Beyond is a global. P1, P2, P3, and P4 are globals. Right? They're all defined outside of functions. Having said that, what P1, P2, P3, and P4 point to, these are pointers. The pointers are globals, but what they point to is on the heap, because it's allocated by malloc. Okay? Useless is a function, just like main is a function. So both of them live in the text area. We don't have any local variables, so we don't see anything in the heap. I'm sorry, in the stack. Okay? So the stack pointer points to the stack, obviously, but we can see everything else exactly as we just mentioned it. The malloc function, it too is in the text area. So before I slide on talking about buffer overflows, let me talk about one other thing. If I build a program that has 4 or 5 .c files, right? The main file, maybe a constant file, a few libraries, right? And I compile these things. They each ultimately form separate .o files. The linker then slams these things together. Each of the original .o files has its own text area, data area, BSS area. Okay? The heap and the stack don't exist because those exist only at runtime. Then, when the linker gets a hold of these, its job is to merge the text areas, to merge the global areas, right? To merge the constants, to merge the global data, to merge the uninitialized global data, to make sure that the final program has the sections exactly the same way. Yes?
I have a question on the heap. So, isn't the size of the heap only limited by the system memory itself? So, like, what I understand about the diagram when it says the heap grows up does that, like, for example, if you're on a 64-bit system with 32 gigabytes of memory and most of it was free, does that mean that the data and the text has to be, like, really far towards one end because the heap is growing up? But I thought, like, but that doesn't make sense because we have multiple programs. I don't think, at least to me, it doesn't make sense if all the data and text is at like one end of the memory and all the stacks are at the other end.
Okay, good question. So how does this work when we have multiple programs and the heap growing and the stack growing? Keep in mind that each process has its own virtual memory. So each process is given the illusion that all of the system's memory belongs to it. So we'll talk about in a few weeks how it is, actually sooner than that, how it is that this illusion is created. Right? It's obviously a conspiracy, because everything is. It's a conspiracy between the processor and the operating system. Okay? But each process is given the illusion that it has all of memory. I should say the processor, the operating system, the memory system. But each process is given the illusion that it has all the memory, so each process believes it has all of this. So each process has its own heap growing up and its own stack growing down. Now, as to your next question as to whether or not you're limited by physical memory, the answer is not necessarily. Right? If a modern system, may have multiple processes running, each process with its own illusion of having the entirety of the address space. And the collection of these processes may in fact use more memory than the system actually has in physical core. Okay? So the response to this, as you may have experienced from time to time on your own system, is that the virtual memory system responds by taking things that aren't being used right now and writing them to disk in order to free up memory. And then when they are needed, swapping them back. And so we have this swapping or paging that allows us to push down that memory hierarchy and make use of disk in place of memory, main memory. It's slower, but it allows us to get a memory footprint that's larger than the amount of RAM we actually have. And so the basic idea, if you think about our memory mountain that we talked about, and we'll talk more about, right, is that we can have a system that performs as if all of its memory is the large, cheap disk at a cost, but performs as well as a system where most of the memory is the really cheap stuff at the top. And the way we do this is by keeping the things we need right now in the fast memory, and very rarely having to swap to the slower memory. Okay. Now, as to your third question, which seem to pertain to what happens with the stack growing up and the heap growing the stack growing down, the heap growing up, the answer is that at a certain point they can collide, right? If you malloc and malloc and malloc and malloc, it doesn't matter how much core your system has, right? In theory, right, you can malloc your way until you hit the stack. It'd be a weird system that had more physical memory than virtual memory, but it's possible. But at a certain point, it is possible for the heap to grow up to the stack and the stack to grow down to the heap. Okay? And that's independent of how many physical frames we have backing things because of that swapping. And that's obviously a problem, because in theory, the stack can corrupt the heap and the heap can corrupt the stack. But in reality, what happens is in the middle, we have our dynamic libraries linked, things that we link in at runtime. And those things that we link in at runtime are linked in read-only. And so if the stack tries to grow slowly downward, it'll eventually try to write on top of that read-only memory, and so that'll blow up before it starts corrupting data in the heap. So in that way, those things serve as what we call guard pages, pages that separate the two. And the same is true if we malloc and malloc and malloc and malloc and malloc and grow the heap up to the point where it hits those pages. So at some level, it's unfortunate because it partitions the stack and the heap, so we can't really get all the way up or all the way down. But at some level, it's fortunate because it provides this protection. Having said that, the protection isn't absolute, because if you just suddenly drop your stack pointer below that, you can skip right past the guard pages and then be in a position to scribble on the heap. Does that answer your question?
Yeah, thank you.
Okay. Any other questions? All right. So now let's charge forward and talk about buffer overflow attacks. The internet worm and the IM war. This is sort of a great story. A couple of these are great stories. So the internet worm. Somebody tell me the story of the internet worm. Somebody knows it. You're smiling, you know it. That's what happens when you smile.
Professor Crosby told us about it.
Yeah.
Okay, so tell me the story.
His roommate did it.
I just know that it was made by a guy called Morris.
Mm-hmm.
And I think it was Harvard, but I'm not sure.
So what do you do?
That it took out like a bunch of like servers and like he got a lot of trouble.
So got a bunch of servers got locked up for it. Okay. Yes.
Was he trying to like figure out the size of the internet and about the letting them without letting other users know that they're being counted, except he had some bugs and caused other users to crash?
That's one story, that he was trying to count the size of the internet. What did it do? Replicated itself. So you guys have maybe played with the finger service on Unix systems. You can say finger space and put in a user ID, and it gives you the directory information about that person. First name, last name, maybe, you know, some title or the year in school or whatever, right? And so you can finger somebody like finger gkesnet.unix.andrew.cmu.edu. Well, the finger service is a daemon, right? It's sitting there, it receives requests over the internet, and provides a response. So there's the stack. You're having too much fun.
A little bit.
Coffee, I see. So there's the stack, right, where local variables are allocated. And basically what happened is the stack was being read with a version of a function that wasn't safe. Okay? The buffer was yay big, and it was reading as much data as the user cared to feed in, with the assumption that the buffer was really big, and the user was only going to make a small request. So basically, you guys learned how the stack discipline works. Okay? You guys learned that if you keep writing, you'll move up the addresses, right? And you'll eventually be able to overwrite the return address. So what you can do, and what you guys will do in the buffer bomb lab, is take actual compiled code, right, the .o stuff, and send it in place of the real request. And then send some padding. And then overwrite the return address with a pointer to your function. And now when the function returns, it actually calls your code instead of the intended code. And so what this obviously did is it took advantage of this type of thing to spread itself. Does that make sense? Because now we're running arbitrary code. We're running whatever code I hand you. So now the machine I just infected is now fingering a bunch of other systems with the exploit code. Yes? A daemon, so just a process that runs by itself. Good question. That's what Unix calls all those things that just sit there and they launch and start and run all by themselves. The daemons do things. I would prefer they call them elves, but you know, the 70s was a dark time. So that's the story behind the internet worm. And then pretty soon, all the machines on the internet, right, were infected with the worm and infecting others. It was bad. But I find actually the story of the instant messenger wars even better. You see, back in the day, okay, most people connected to the internet via dial-up. Okay, actually, back in the day, right, we started out with people who were connected via computer, probably connected via CompuServe. Right, that was sort of the consumer bulletin board service for the average person. Okay, you dial up to CompuServe, and they would have a bunch of forums. And then you could talk on forums to other people, and there was some advertising that was being paid for on these forums, and that was as cool as it got. Okay. You know, you could email, leave messages, and whatever. And so then as we started getting more and more internet connectivity, okay, you were able to send email to people even if they weren't connected via CompuServe, right? More and more people had dial-up service, and AOL became a big player. And they were sort of a major portal that had much more graphics than did CompuServe. It was a much more advanced looking portal, right? And so you'd pay AOL, you know, whatever it was per month, and you'd get dial-up connectivity that would include, you know, internet connectivity as well as, most importantly, connectivity to AOL's portal. And you know, you guys have no doubt seen in popular culture, you know, the replays of their commercial. You have mail, right? And so AOL had developed this huge user base based upon their portal, which was very, very rich, right? And a fairly decent package for you know, for dial-up connectivity and sort of ubiquitous connectivity. Like if you traveled anywhere you were, you know, you could dial up to AOL. It was, you know, sort of good national coverage. And so by this time, 99, right, AOL was, right, they were on a bit of a nosedive, okay, because fewer and fewer and fewer people were paying for dial-up. Instead, people were using things like cable modems that just provided better service. So AOL was shedding subscribers pretty quickly, I think, as people adopted cable modems. And eventually they converted themselves to a portal service, right? They basically got out of the modem business and basically tried to cause people to go to their site, driving traffic, advertising, name the game. But at this point in time, they were sort of in this weird space where they were still selling a whole bunch of dial-up modem lines, but they knew that wasn't the future. One asset they had was that they had a huge number of subscribers. And they decided that they were going to protect their subscribers, because they knew that modem revenue wasn't going to be the long-term game. So they basically made AOL free. Okay? You paid for a dial-up subscription if you wanted one, but it didn't get you anything extra. You could go and get the AOL portal whether or not you had AOL in some sense. And this was great because a whole bunch of people were using AOL to begin with, because it was a great national walled garden type of service. And then, right, people had no reason to leave because it became free. So AOL now tried to capitalize on having this large number of users. One thing that people really liked was instant messaging. Because if you wanted to talk to somebody, they had an AOL account. So you could IM whoever you wanted on AOL. Like anybody above the age of 12, right, you could IM on AOL. Maybe 10. In some cases, 6-year-olds, but with parental supervision, or whatever it was, right? And this made Microsoft really, really jealous. Because they were trying to start up a competitor called the Microsoft Network, MSN. Okay. And the problem was that all the users were over on AOL. And no matter what they did, users didn't want to move, because all their friends were on AOL. Like if they go to Microsoft, there's nobody to talk to. So, in classic example of business strategy, if you can't build it, steal it. Microsoft made Microsoft Messenger such that it worked with everybody on Microsoft's network, and also everybody on America Online's network. They just had their messenger talk to AOL servers. So now if you had MSN, like you couldn't lose. You could talk to AOL, you could talk to MSN. This really pissed off the people at AOL, right? Because their instant messenger was advertising driven. That was their plan, right? There was a little ad at the bottom of the messenger that generated revenue to pay for their servers. And now Microsoft had their messenger that didn't show their ad and didn't pay for the AOL servers that were proxying the messages. But there was no authentication built in or anything, right? There was no reason to in the day. So AOL changed the protocol. And Microsoft changed the protocol to match. And they went through several iterations of this. But AOL had a problem because every time it changed the protocol, it had to push updates out to its users to accommodate the change. At one point, the only way they had to do this was to buffer exploit their own instant messenger. Because they needed to make sure that the update happened right now, not some scheduled update, or people would have downtime. And so AOL buffer exploited their own messenger in order to push the update out. And the slides, in my view, slightly out of order. But here's a really cool message. So Microsoft got annoyed that AOL was, buffer exploiting their own messenger just to keep Microsoft from stealing their services. And so somebody inside Microsoft sends this letter to a journalist. The person pretending to be somebody called Phil Buckley, maybe actually was, I don't know, but claiming that he's a consultant. This message was discovered to have been sent from inside the Microsoft complex. To this journalist, Mr. Smith. I'm writing you because I've discovered something that I think you might find interesting because you're an internet security expert with experience in this area. I've also tried to contact AOL but received no response. I'm a developer who's been working on a revolutionary new message client that should be released later this year. It appears that the AIM client has a buffer overrun bug. By itself, this might not be the end of the world, as MS surely has its share, but AOL is now exploiting their own buffer overrun bug to help in its effort to block MS Instant Messenger. Since you have significant credibility with the press, I hope that you can use this information to help inform people that behind AOL's friendly exterior, they're nefariously compromising people's security. Go Microsoft. No doubt. Okay, so now let's charge forward and see how this works. Here we can see we have a function called getS. You guys may be familiar with it. You pass in a buffer, and then it sits there and reads characters into the buffer you pass in. The problem with getS is that it'll read characters until the user hits enter, regardless of the size of your buffer. So if your buffer has room for 10 characters, and the user enters in 500 characters, and it's going to write the first 0, first, second, third, fourth, and then just keep writing past the end of your buffer, overwriting things. Destroying stuff until either, it's done, or hits some page that's not mapped, and thereby you get a seg fault. Similar, problems exist with things like string copy or string cat that don't have sizes. Yeah.
Where did it specifically only get room for 10 characters?
Well, this buffer that's being passed in is of a particular size.
Oh.
So if somebody creates a string called buffer, a char buffer of 255 or 256, right? Then that gets passed in. Its size is 256.
Okay.
Does that make sense?
Yeah.
And then this thing will sit there and spin 0, 1, 2, 3, 4, 5, 254, 255, 256, 257, 258, 259, blah, 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 right? Until this thing returns new line or fails.
And because it's a char star, it's putting that on the heap?
It's pretty well. That depends where this is, right? We don't know where that buffer is. That buffer might be a global variable allocated in global space. It might have been malloc. It might be on the stack. But in any case, it's overwriting it.
Okay. Thank you.
You're welcome. That did answer your question, right?
No, it did, yeah.
Okay. So, here we can see an example of a 4-byte buffer being fed something large. Ta-da! 4-byte buffer, each 7 characters. Seg fault. In this case, because it goes beyond the end of the stack and it doesn't happen to be mapped. Okay. If you take a look at it, right, what do we see going on here? We call getS, and then we call putS, right? And getS is going to sit there and do what you think it's going to do, right? Here's a picture that I think is going to turn out to be useful. We have a function now called echo. Yeah?
Could you explain 2 pages ago why that seg faulted?
The reason it's seg faulted, how about we stick here for just a second? I think you'll see. Here now we have a function called echo. And now we have essentially the same code, but this time inside echo. This means that buff now is a local variable. Buff is allocated on the stack because it's a local variable. So now you can see that we have the caller main, pushes the return address on the stack, calls the function. There are no arguments here, so there's no argument build area. This function itself saves the EBP, saves the EBX, right? And then we have its local variables. In this case, just buff. When we do getS, it's going to write A, B, C, D. Now watch. If we don't stop there, E, F, G, H, I, J, K, L, M, N, O, P. You see how that goes up the stack? From low address to high address. Okay. So why did it seg fault? Well, do you see how this is overriding from low to high? See that? Imagine that was a global. Imagine that was a global variable down here, and it kept writing upward. Eventually, it would get into that hole between the stack and the heap, and the memory there isn't allocated, and that's what a segmentation violation means. It means you're using address that hasn't been allocated yet. It's not allocated until we call malloc, and that heap grows. Or we call a function, and we push it onto the stack. Does that make sense?
Yes, except for it said that, like, it didn't seg fault when there were 7 inputs, but it did when there was 8.
Yeah, and we don't know that, right? It depends where that variable is in the global space, the heap space, and what comes after it. So when you make mistakes like that, the results are very non-deterministic. It really depends on exactly the circumstances. Does that make sense? Because there may be another variable right after that, and you just overwrite that variable. That won't seg fault. You've heard me say it before, right? Regardless of your religion, right? Seg faults should be evidence for you in the pile of things that prove that in fact there is a God and He loves you. right? Because if you get a seg fault, right, your program stops when it has this error. And you can debug and see like exactly what operation overwrote memory there. But if it doesn't seg fault and you just overwrite some values, your program can churn on for a very, very long time generating incorrect results. Does that make sense? So seg faults are actually really good because they allow you to sit there, get into a debugger, let the seg fault happen, and then see exactly what caused the seg fault. This write caused the seg fault. Why did this write cause the seg fault? Oh, it's writing into this buffer. Well, how big is the buffer? How many bytes did it write? Oops, I see my problem. So seg faults are great. Overwriting variables? Not so good. Make sense? Did that answer your question? Okay. So now we can see, right, how overflowing a buffer overwrites things, important things. And now we can see how we can exploit this. Okay? Take some code, compile it, get the object code. Okay? Then, instead of whatever input this thing expects, write the object code, which is now going to overwrite things. And make the code the right size, and add enough padding that you write program code, 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 buffer, padding, 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 and then overwrite the return address with the address of your code. Now when it pops the return address off to return, it's going to go to your function, not where it belongs. Yes?
How do you know how big the buffer is?
How do you know how big the buffer is? The answer is that you guess. You either have the source code, or the compiled code and can figure it out by looking, or you guess. You just do a lot of attacks until you get one that works. Make sense? Okay. And so now we see this overwriting happening. Okay. Where we've written into the buffer, and so far we're fine. Okay. And then we overwrite this, and now we've overwritten the return address. Okay. And now you see the input of 1, 2, 3, 4, 5, 6, 7. Okay. Blink, blink. 8, blink. See that? How we just overwrote this element, the 8, 8. 0, 0 becomes 8, 8, right? Now we've overwritten this, 6, 7, 8, 9. Okay. And now we see how this works. Exploit code, pad, the address of our exploit code. And that's how the worm worked. Yeah.
So this exploit code is like you would input code into like the string, and so then it sends it to some random address that you pushed onto the stack through overwriting character.
Well, you're not going to push it onto the stack. What you're going to do is take the code and compile it, because you can't put C code there. It has to be like machine code, right? Object code.
Yeah.
So now you get the object code, okay, and now it's just bytes.
Yeah, and so now you just put that in as characters?
Yeah, because it's just.
Because like A is like not going to have sense.
So yeah, so you just, at the end of the day, a character is just a number.
Yeah.
So you just send it that way.
So we would compile our code on something else on our own little laptop.
Yes.
Find out what the byte code is. Change that to say it was asking for ASCII value, the gets function, and then we would just write that byte code basically in ASCII values. And then
So the question is, do we write the byte code in ASCII values, and do we compile it on our own laptop?
we could hypothetically use ASCII values. And maybe
Right. Well, so let's back up. First of all, what you compile on has to be the same architecture, because it has to be the same assembly.
Yeah.
So if your laptop's a Mac and you're trying to exploit an Intel server,
Well, yeah, but why would I have that?
right? So I just want to. You may know that, but I wanted to clarify that for everybody. Second thing, you don't need to convert it to ASCII values. If you're connecting to it, right, your program can just write the bytes, and the read will just read the bytes.
Okay.
The ASCII is just one way of rendering those bytes.
Okay.
Does that make sense?
Yes.
Okay. You wouldn't want to, for example, take the binary 0 and convert it to ASCII 0, because that would no longer be machine code. Okay. So we write our exploit code, some bad padding, and then we overwrite the return address with a pointer to our exploit code. And that's how the worm worked. Exploit code, padding, new return address. And it was just passed in with finger. Okay. So what to say? There are all sorts of classic examples about this, right? You know, from whitehouse.gov to Microsoft sites, whatever. And so a code exploit might look something like this, right? Going to a web server, get some page, and then the parameters that would normally be going to the CGI program are now exploit code. Yeah?
Similar question to the last one, but how do you know the return address that your code is going to be stored at?
The question is, how do you know the return address your code is going to be stored at? Initially, you don't. Okay? So you have to guess. I mean, if you have the server code and can analyze it, then you know. Okay, because you can look at it and say, okay, you know, this function is running on this. Here's the code for this function, and it was compiled with this compiler, which uses these alignment rules, running on this architecture. So, for example, when the internet worm was written, right, all that information was known. Right, he knew what machine he was writing for, what the hardware rules were, what operating system it was running, so what version of Finger it had. He had the Finger source code. In that case, everything was known. So then you can just figure it out. If you're attacking some random server on the internet, right, maybe you have the source code because it's an Apache web server or something. Maybe you don't. If you don't, you just guess. Because, like, really think about it, like, how big is the average stack frame? Like, probably not more than a few local variables, right? Probably, so you can try relatively few possibilities. And so you just do that. You write a program that tries the exploit with varying amounts of padding until it gives you something, and then it says, then you see that your function's called. Now you know the size. Now you can put your real exploit code in there. Does that make sense? Yeah.
Does this mean that our exploit code, the length is limited by the buffer and how little padding we want to give?
Does that mean that the length is limited by the size of this? Well, there's a whole long stack frame. And so maybe it's not the first function that returns, maybe it's the second or third in that chain. So you're not necessarily limited that way. But you can only write upward. There's no way of forcing it to write downward. Does that make sense? Okay. Avoiding buffer overflow. It's actually not hard, right? For example, instead of using getS, we can use fgetS. FgetS is the version designed for read from files, but we can just use standard in as the file name, and that works as a substitute for getS, except for the fact that it takes two arguments, other arguments, a buffer and the length of the buffer, right? More properly, the maximum length of a string. So now we can't overwrite the buffer because it'll stop when it gets to this point. Okay? And so as long as we do things where we're actually limiting the size of input to the size of the buffer, we can't get indigestion by being fed badly. There are some system level protections. So to the point of trying to figure out how things are going, one thing they can do is at system level is randomize them. Start the stack at different offsets every time every time the program is run. Then you're going to have a hard time figuring out what the return address is, right? Non-executable code segments are the best idea. Simply don't allow code to run out of the stack. Make the stack readable and writable, but not executable. Right? This did not exist in the 32-bit architecture until the original x86 architecture didn't support that. The newer 64-bit architecture does. There are canary values. Basically, you can ask GCC to write a magic number into the stack, and then to add code that looks for that magic number. And then if it doesn't find it, it knows the stack has been exploited, or at least the stack has been overwritten. Okay? And then GCC will die and produce an error message. Okay? And if you look at it, right, it does the comparison. And if it matches, it jumps past it to 8048683, right? Yeink. Otherwise, it jumps to the error message. Do you see how that works? Look for our canary. If we find it, jump to what we want to do. Otherwise, fall through to our stack slamming message. Okay. So we call the function. Now we check the stack. Now we jump or fall through. And now you see here we have the canary. And we have our buffer. Okay. So we retrieve the canary from the stack. We retrieve, we hope, is the canary from the stack. We compare it to this. Okay. This is our canary. This is the value we got off the stack that we hope is our canary. This is the well-known value. This is the value that we think is the canary, because that's what we wrote there, but could have been slammed. This is in a register, right? Okay. Now we do the comparison and jump.
Does the compiler put that canary in, or do we put it in?
You could write this code yourself, but if you give it, it's formulaic code. It looks the same every time, right? So if you add the protect all flag, then GCC does it for you.
Okay.
And the important thing here is that the canary isn't on the stack. Yes?
Is it possible that the value doesn't get overwritten and still we have overflow?
Is it possible the value is not overwritten, that you don't have overflow?
Like with checking for it and it's still there, but still we have buffer overflow.
It's not possible that the value is still in the stack and you don't have overflow. Okay, because you have to write through the value to get there. It is possible, however, that you rewrite the value, that you either rewrite the canary, or that you write code that changes the canary. It's not perfect. Yes?
Because it's writing 0, 1, 2, 3, would you have to supply the machine code in inverse order? Like if you want to do push 6, you have to give it 6 push?
No, because when you say it's writing 0, 1, 2, 3, it's writing from lowest to highest, which is the natural way that things would be written.
Is it because of little endian?
The endianness is transparent to us because that's the way the machine thinks. It's like if you happen to write in a language where you write from the right to the left, you don't have to reverse the word order because you're writing from the right to the left. Certain forms of Chinese or Hebrew, right?
That makes sense. I was just confused with how it was writing up.
Well, it's writing up because it's writing from lowest address to highest address. Element 0, element 1, element 2, element 3, element 4, right? Lowest to highest. Good? Excellent. Okay. Okay. And so, here we can see the canary in place. Boom. And off we go. Okay. This slide is silly. Worms versus viruses, who cares? Malware. According to the slide, a worm is a program that can run by itself and can propagate to other computers. A virus is code that adds itself to running programs but doesn't run independently. And both are usually designed to do evil things. Rarely do you get a virus and, are happy about that. Okay. Any questions? I think this lecture is slightly short today because I think I covered more than I was supposed to last class. Details. I was on a roll. Have a great one, everybody.